Welcome everybody to the third edition of our online show, TPRC Talks. My name is Aniek van Damme, and together with me are two guests here in the studio, very excited to share their experience with you. Live from the lab in Enschede, we invite you along into the world of the Thermoplastic Composites Research Center. And today we'll talk about the welding of thermoplastic composites, a hot topic. So let's move to the guests here in the studio. Let me introduce you to Wouter Grauve, Assistant Professor at the University of Twente. Welcome, Wouter.
Thank you. Happy to be here.
Hello. You work at the University of Twente. What is the link to the TPRC?
Well, to be frank, I feel quite at home at TPRC because I worked here for 6 years before I moved to the university. And when I started here, the lab was still empty. And when I look around now, it's completely filled. So I was really happy and really encouraging to see the growth the center has experienced over the last years. And in my current role as a university assistant professor, I supervise PhD students and master students.
Very nice. Erik Kramer, Senior Research and Business Developer at the TPRC. Welcome.
Thank you. Looking forward to another exciting episode about thermoplastic composites.
Nice. And how are you related to the TPRC?
Well, I've been involved with the TPRC for about 5.5 years now. And the past 4 years, I've worked on my PhD, which was related to defects in thermoplastic composite processing. And since the beginning of this year, I'm a senior researcher, and now I'm also working on business development.
Great. Welcome. Nice to have you here.
Thanks.
Well, in our previous episodes, we talked about the future of thermoplastic composites and how stamp forming contributes the increase of manufacturing of bigger aircraft. And you can rewatch the complete shows on the TPRC's YouTube channel. Yes, so today we focus on welding. Let me introduce you this TPRC talent, Yannick Buser, PhD student. He's on the floor and he'll gonna explain to us what these machines are for.
Thank you for the introduction. With these machines, we can weld thermoplastic composites via local heating of the material.
Thank you, Yannick, and we'll hear more from you later on in this show. Well, first we have a question for you. We want to know whether you are a welding rookie or an advanced professional. So we invite you to fill in this poll, and then we will know who is looking at this show. That would be great. Wouter, what do you think?
Well, I believe our audience is quite competent, so I expect a lot of experts in this particular case.
Yeah? Do you share that?
Yeah, I agree. Yeah, definitely. Hopefully not too expert, so people will still learn something today.
Okay, well, we're very curious. How did you, when did you learn welding for the first time?
Well, when I came into contact with thermoplastic composites, that's the first time I heard about weldability, and I didn't really know what it was at that time or what the specific benefits were. But, well, experience it within the TPRC, you see that it's really a big topic, and it's really a good benefit.
Nice. Well, in the meantime, I got the results. We have 60% of brand new welding. How do I say that? Welding rookies.
Okay. That's excellent.
Beginner starters.
So a lot to learn still.
A lot to learn. 30% are advanced. No, let's see. What did we have? We had beginners, advanced, and experts.
Okay.
Yes. So the big group is new to the subject.
That's good.
What do you say, Wouter?
Yeah, I think it's very nice. So we've got some nice insight, I think, from people, to which this is very interesting for this particular group, I would say.
Great. Well, thanks everybody for participating. And before we turn up the heat and talk about welding, please note that we have the chance for some interaction. So if you have a question to my guests here in the studio, please don't hesitate to ask it through the Q&A, and I'll make sure there's room answering them at the last part of the show. Well, guys, why are we talking about welding in general and on induction welding in particular?
Well, we've come a long way into producing single parts from thermoplastic composites. And nowadays we can make three-dimensional parts with exceptionally high quality. And if you look at the industry, they are going for more and more advanced integrated structures to reduce weight, but also to reduce fuel consumption. And that's where we need joining of these parts. So we need welding to join these single parts.
Great. Yeah, that was something we all already talked about in the last episode. And now we're going to go deeper into this subject. Great, thanks. And we have some exciting news to share in this episode.
Yes,
Wouter, please enlighten us.
Yes, indeed, Annick. So we've secured quite a big funding for a large program dedicated to welding or fusion bonding. So we will work together with a total of 15 researchers, 6 universities, 4 research centers, of which TPRC obviously is one, and over 25 industrial companies on the topic of welding. And the basic idea is to develop the tools and technologies required to come to predictable, reproducible, and cost-effective welding technologies.
It's big, right? How happy are you?
Yeah, I'm really excited. So we will work on this for the coming 5 years. There's many people involved, so I'm really excited to start, actually.
Nice, great. Well, later on in this show, we'll go more into detail and talk about the added value this research program can have on global innovation. Well, in the upcoming 45 minutes, we will talk about the different welding techniques the research TPRC is focusing on, and we will talk to partners, Boeing, Spirit, and KVE. But first, let's start with the basics. First things first, Yannick Busser, how does welding work?
In our typical manufacturing process for thermoplastic composites, we take tape from manufacturer as input material where we cut it to size and we stack it. And then in an autoclave or a press, we typically fuse those different layers as a stack together in the right time, temperature, and pressure. And what we do here is we apply this temperature globally by bringing the entire stack into melt where all those layers are fused together in the end. So now with welding, we apply the same principle of fusion bonding by taking 2 finalized components, fixing them in a mold together and applying the time, pressure and temperature now locally to melt the interface of the 2 parts while they will consolidate into one singular structure in the end. Applying this temperature and pressure locally, therein lies the challenge, and that's the key difference here. Now, different welding technologies exist for thermoplastic composites, and they mainly vary in how this local temperature is applied to the joint interface. Takeaway, however, is that welding by fusion bonding is simply very natural to the manufacturing process of thermoplastic composites.
What are the advantages of welding over other assembly techniques, such as adhesive bonding and fastening?
Well, if you look at these others too, for example, fastening, adhesive bonding, they are quite time-consuming and costly as a result of that. So for fastening, you need to drill holes, you need to apply the fasteners. Or for adhesive bonding, you need to do, for example, surface preparation, which is also costly and time-consuming. Welding does not suffer from these disadvantages, so that's really nice. And in addition to that, if you weld a structure, you create a monolithic structure. So it's one material, which is really attractive, for example, in terms of certification, but also in recycling, for example.
And does a successful welding technique also have advantages for the part itself and for the final structure?
Yes, definitely. So we know that composite material gets its stiffness and strength from the continuity of the fibers. Mm-hmm. And if you look at conventional ways of joining parts with fasteners, for example, then you need to drill holes and then you cut the fibers. So you lose your stiffness and your strength. Mm-hmm. With welding, you don't have that disadvantage. And another advantage is you don't have to use any fasteners. So that means your part will be lighter.
Do you have something to add to that?
Yeah, but like I just said, I think this is important to stress here. If you look at sustainability, if you look ahead, we need to recycle our structures. And if you don't have to remove any fasteners, adhesive or primers, that's really an advantage in terms of recycling. So that's an added benefit, I would say.
Yeah, I can understand. Well, let's time to talk a bit about the different welding techniques. But before we do that, what do we need for a good weld?
So in essence, welding is really simple. Basically what you need, like Yannick also explained very nicely just a minute ago, we need heat, pressure and time. So basically when we want to weld structures, we need to put them together, apply pressure, heat the interface, and then wait, simply wait. And there's different ways to do this. And all these different technologies which are available, they're different the way heat is generated at the interface or pressure is applied.
So what welding techniques do we know?
Well, for instance, we have ultrasonic welding, and here we apply a high-frequency vibration to our material. So locally, it gets heated at the interface. Well, this is a very fast process and typically very well suited for spot welding, for example. And it's a bit difficult to, well, because it's a discontinuous process, but our colleagues at the DLR and at the Technical University of Delft are working on making this process continuous. And
You do that with a small hammer, right?
yeah, exactly. Yeah. But it makes an awful lot of noise, especially when you're young and you still have good hearing. But with good engineering, we can overcome this. Yeah.
Okay, very good. Okay, that's the first one, hammer time. What about the second one?
Second one could be, for example, resistance welding, where you use a metal mesh which you place in between the two parts you want to weld. And if you then apply a current to this mesh, it will simply heat up. So very much like an old-fashioned light bulb, for example. And you use this heat to soften the matrix or melt the matrix material into the interface and allow it to fuse it. So this is actually quite a mature technology. It's being used. And an additional advantage that you can use it for quite flexible shapes, for example, welding area and welding sizes, which is really nice. The main disadvantage is that this mesh remains at the interface after manufacturing, and it's a bit unsure what this will do on the long-term performance. In addition to that, it's also quite difficult to weld carbon fiber reinforced composite using this way because carbon fibers themselves are electrical conductive.
You say it's already been used. Is it flying?
Yes, flying. So Airbus, we've got a small demonstrator here, which I can show. So this is a leading edge of an Airbus aircraft manufactured by our colleagues from Fokker. And this is actually being manufactured using resistance welding. So it's actually flying as we speak.
Well, great. Now we've covered ultrasonic welding, resistance welding. With the third one, we go a bit more in depth as the TPRC is doing research on this one. It's called induction welding.
Yes, well, you might actually have this technique at home because you might know it from induction cooking. So a lot of people nowadays have an induction plate at home. And the heat is not generated in the plate itself, but it's generated with a coil. And this coil generates an alternating magnetic field. And this magnetic field gets absorbed by the pan. And this generates an electric current inside the pan, which will convert to heat. So the bottom of your pan is actually the heat source in this case.
Yeah, so your pan doesn't get hot itself.
Exactly. No, the plate doesn't get hot.
True.
Yeah.
That's important. Great. So we had induction welding, resistance welding, ultrasonic welding. Let's switch from the kitchen to the lab. How does this work in a lab?
Well, it's basically the same thing. You need to generate an electrical current inside your material, and this will only work with conductive fibers. So it doesn't work with glass fiber, but it does work with carbon fibers. And it's a good thing that most of the fibers used in the aerospace industry are carbon fibers. So we can actually apply this technique.
Great. Well, if you have any questions for these gentlemen about this topic, please don't hesitate to ask it through the Q&A. And let's go back to our expert on the floor, because Yannick is actually doing research on induction welding. Let's see what his research is all about.
I'm Yannick Buster. I've got a degree in mechanical engineering and I'm a PhD student at the TPRC. My research is focused on induction welding, where I take a look at the relation between material microstructure and the process itself. So right now, I'd like to take you along in this process by looking at the actual heat generation and the fundamentals of it during induction welding. Okay, so let's explain how heat is generated in induction welding. First of all, induction welding is a very clean process, as no additional materials are required to form a bond. Heat is generated directly within the material, and that makes it very fit for recycling. So for induction welding, we need two main components, one of which is the source, and the other is a susceptor. The source emits an electromagnetic field once an alternating current is applied to it. And the susceptor is any material which can conduct electricity, which will react to this alternating electromagnetic field generated by the source. In our case, that's a carbon fiber reinforced laminate. So once this laminate is held in close vicinity to the source and thus in the intense field, loops of electric current will run through it. These currents we call eddy currents. The presence of eddy currents can be illustrated via this simple experiment where we've got a magnet and a piece of aluminum. What we see now is not magnetism, but the actual induction of eddy currents, as the moving magnet creates a changing magnetic field. A similar thing happens during the actual induction welding process, where in the experiment our coil is represented as a magnet and the aluminum was representing the carbon fiber plate. So in the experiment, the moving magnet would not result in large heat up in the aluminum, but imagine that now in the actual process, the field is changing at a very high frequency of 300,000 times a second. And at the same time, the field is way, way stronger. So the induced loops of electrical currents, the eddy currents, those will be met with the inherent resistance of the material, heating up the assembly locally. I can show you the actual heat generation through eddy currents with an experimental setup that I built for my research. In this setup, we use a thermal camera to monitor and record the heat generation inside the material and display it on a computer. As we can see, the heat is generated very rapidly as the material heats up to over 100 degrees easily in a matter of a second. The challenge is to understand how exactly heat is being generated inside the material, and that requires a lot of fundamental research. The complexity is that we've got a network of conductive carbon fibers inside an insulating polymer. That's where our expertise comes in, because with our research, we aim towards application of induction welding on large structures in commercial aircraft. This is what an actual production setup could look like, where via a dedicated tool, we apply the right time, pressure and temperature to the material when we run such a coil alongside the weld line. And then in the end, we could obtain an assembly just like this. I experience a lot of joy in cooperating with my colleagues and the TPRC partners on this project, with the aim to eventually adopt this process on large-scale structures in industry.
Yes, like Yannick is pointing out in this video, we want the heat exactly at the right spot. And with induction welding, we create current within the material. But how do we get that heat exactly at the interface?
That's one of the main challenges, and physically this is not really possible. So we will always generate heat in our materials, whatever you do, unless we use an energy director or we change the materials we want to weld. And this is not something we would like to do. So as a solution that we want to control the welding process and control the temperature distribution in our weld to such a degree that it gives us a proper weld. And this is quite challenging. In practice, that means that we often need to extract, for example, heat from the surfaces, which can be quite difficult to do.
Okay. Well, later on, we will talk to partners Boeing and Spirit. But first, I want to bring Maarten Bach in from KVE Composites to hear about their perspective and to hear what they think about induction welding. Hello, Maarten. Hello. Good to have you on the show. Welcome.
Hello. Hello. Nice to meet you all.
Hello. Can you briefly tell us a bit more about your organization and vision?
Yes, of course. Well, KV is also a company based in the Netherlands. We are on the west side of the Netherlands, and we are a relatively small design and build company, focusing both on thermoset and thermoplastic applications. And for the thermoplastics, we have been working on the induction welding technology over already 20 years. I was just reviewing that one of the first projects we started together with the Boeing company in 2001. And we've come a long way. So the induction welding technology you see at the TPRC, it's actually the setup which has been developed by KVE, where one of the things is that we have technology patented, because the complexity is indeed that you have to get the heat exactly at the center of the joining of the two materials. And we use a heat sink material on the top, which is transparent for the magnetic field, and that cools the top surface, and that allows us to generate the heat exactly at the interface. So this technology has been developed over the years, and there were some projects where we were so, let's say, successful and in the end to display this technology that it was in 2007 seen by Fokker Aerostructures, and they have used this technology together with us to make a demonstrator, and after this, develop this into flying applications. So the technology is at this moment qualified in flying on business jets, so on the Gulfstream G650, where it is placed on the rudders and elevators of the aircraft. and also on an aircraft of Dassault. The Dassault F6X. So this is for us really some of the exciting things that I know that there are aircraft flying around using our technology.
Nice. That must be a great feeling.
Yeah. Well, I work now 1 year for KV, so I wasn't part of that team, but still, I'm proud to be part of that company. And at this moment, one of your other questions was where are we? We're looking into the applications are using fabric material. And Yannick also indicated what he just showed, it was a fabric material. And with fabrics, it is relatively easy to generate eddy currents within one ply. But the trend in the aerospace is going into unidirectional material. And this allows for quicker automation of the processes. And so this is seen as, let's say, the next phase of aircraft manufacturing. But with UDs, you have the ply, all the fibers are in one direction. So it's more difficult to generate eddy current inside one ply. So that only happens when there's, let's say, an interface with the ply, which is under another angle. And that makes it much more complicated. So we, at this moment, are looking into developing the technology to the level that it can also be applied using UD materials. And that's also where Yannick currently is focusing on.
Nice.
So looking into the heat mechanisms with UD materials.
Great. Well, while you were telling this, I saw the gentleman here in the studio nodding. Do you feel this the same as Martin is sharing, the whole development where it's going to with the UD? Erik?
Yes, definitely. We see that automation of processes, it's a trend, and it's becoming much more important nowadays. So this involves unidirectional material, and as Martin says, it's a challenge to combine this with induction welding.
Yeah. Well, how valuable is the TPRC's research for you, Martin?
Well, I think that's a very good question, because we are a small company, so we have developed this technology in-house, but we are a small team, and we also have our, let's say, commercial applications. But the research being done at the TPRC, it's on a much more fundamental level to really understand how does this material heat up, and to really look at the basics of that and really dive deep, and that supports us to better understand how this technology can be applied. So for us, it's really essential to have a partner like TPRC to support us. And so we also really cooperate with Yannick on this. Yeah.
Nice. Well, how does TPRC contribute to your business then?
Well, in such a way that we believe that the next generation of aircraft will be using UD materials. So we look into applying our induction welding technology to the market. But for us to develop that technology to be able to produce the same kind of quality parts, we need to understand the small changes in the material, the effect of this, and that's the kind of research which has been being done at TPRC. So that's really the fundamentals for us to build towards commercial applications.
Yeah, and you already talked a bit on this topic in your first answer, but how did you get into induction welding?
As a company?
Yeah.
Well, that's actually a good question. So KVE started with two founders, and one of the founders, he currently works at Torre, Advanced Composites, but there was kind of a thermoplastics team and a thermoset team and kind of, let's say, product development team. And the thermoplastics team, they have done some stamp forming, but then the idea came across like, wouldn't it be nice if we can weld the parts together to make a welded assembly without rivets, without fasteners? This will be a tremendous improvement, which is only possible with thermoplastics. So in that brainstorm, they found out that induction welding as a technology that seems the most promising, because you are not in direct contact with the material, but you use, let's say, a contactless method and you can really direct the energy towards the interface. So that's how that development got started, and then there were a lot of research projects established. So that's why I think it already took us around 7 years to get the technology towards, let's say, the first large demonstrators. But we believed in it, and we kept on continuing. And I think also last year there was the anniversary of 10 years of TPRC. So the last 10 years there's been a massive improvement on thermoplastic. So now I think we really see a growing maturity of the technology, and this allows us to move to more flying applications. And so I think we've just been relatively an early adapter of the technology.
Great. Well, thank you very much for your time and sharing this experience with us.
Thank you so much too.
Well, there are not a lot of welding setups in the world. There are 4 or 5 welding setups, right? Erik, can you tell about that?
Yes, that's true. It's not really a mature technology, and it's quite difficult to understand the fundamentals. But one of the setups we have here at the TPRC.
Okay, very good. Well, what are the remaining challenges when it comes to induction welding?
Well, as Martin said, you need to heat the material at the interface. So you want to apply the heat locally. And we have some different methods for this, each with their own advantage and disadvantage. But in practice, we still need trial and error to get the process right. And we need a lot of material characterization, and that's all quite expensive. And one thing which is also important is that there is no margin for error. So the weld has to be right, because you cannot unweld it anymore.
Well, last time we talked about simulations. Now you mentioned that when it comes to induction welding, we still rely on trial and error. Can't we just use simulations as well for induction welding?
That's a very good question. And of course, that will be ideal. But the simple answer is no, because we don't have the simulation tools at the moment. So there are no tools available to predict the performance of the assembly, so the weld strength or weld toughness. And there are no tools available, simulation tools, that allow us to predict the simulation process itself. So that's a real disadvantage. And that's also why TPRC and also within Enlighten, we focus so much on development of simulation tools. And I want to add to that a small thing. So trial and error in itself is quite difficult already. It's time consuming. And in the case of welding, it is even more difficult because we have a sort of black box process. So we have our 2 parts, we put them in a tool, we close the tool, and then we weld. And then we basically have to hope and try that the weld is good.
It's time consuming, but it also costs a lot of money, right?
Yeah, exactly. So that makes the process difficult to implement in practice, especially if you want to make a new assembly. You have to go through all this process again. So that's really a challenge.
Yeah. Well, what will Enlighten bring?
Yeah, so within the research program Enlighten, we try to address both of these things, basically. So the first thing we would like to do is develop the predictive simulation tools for welds. So that means that we would like to predict the performance of an assembly. So that means that we need to predict the strength or the toughness of a weld. And this is not straightforward, because we know that the performance of these materials depends on the microstructure. And this microstructure, again, is formed during the process. So if we want to develop process models for strength, we also need to develop process models themselves, which is challenging. Alongside that, we also need to develop the inline monitoring tools for different welding technologies, which in itself is a challenge as well, because you cannot use sensors at the weld interface, which is which cannot be used in reality. So that's something we would like to develop within Enlighten. If you combine process modeling and inline monitoring, maybe we can get to process control. That will be the holy grail for welding technologies, I would say.
Would you say it's mostly a black box?
Yeah, I think we know what's in the black box, but it's difficult to look inside. So we're not completely blind, but it's not easy to optimize the process without the tools we have at the moment.
And with Enlighten, do you think we can open that black box?
I think we can make a very big step. So we'll have 15 researchers, which will be supervised by very enthusiastic personnel at different universities with different backgrounds and different expertise. So I'm really confident that we can make a really big step. So I'm really eager to start and see where we'll end up, basically.
Nice. We'll see all the partners involved in the Enlighten project.
Yeah, indeed.
And how is that important knowledge translated to the industry?
Yeah.
Well, a lot of models are developed within the Enlighten program, and whenever possible, these will be commercialized as well, and these will be shared with the industry. And alongside that, there is also a work package on demonstration. So the universities of applied science and the research centers, of which the TPRC is an important one, they will work together on this. And also they are looking at a lab scale to provide the infrastructure for pre-processing testing, which the industry can use.
Okay, so the whole value chain will benefit from this program.
Yes, exactly. Yeah.
Great. Well, let's talk to other partners to hear their perspective on induction welding. First one is Andy Meijer. She's the Engineering Manager, Advanced Research and Technology of Spirit Aerosystems. Hello, Andy. Welcome. Nice to have you on the show.
Hello. Thanks for having me.
Andy, Spirit is a supplier to Boeing, and you're now exploring welding and finding out it's not as easy as it always seemed. You're relatively new to the field of thermoplastic composites. What's your take on welding?
Well, we're not exactly new to thermoplastic composites, having worked on it. Spirit worked on it in the 90s as Boeing, but there's certainly a resurgence. We've had our ebbs and flows, and in the past 10 years or less, supported by TPRC, there's been quite a resurgence in our internal R&D efforts. And that's primarily, as you mentioned, we do supply to Boeing. The single aisle aircraft is critical to our business. And so the high rates that are needed that we anticipate with the next composite single aisle aircraft is not necessarily compatible with thermosetting composites that we are experts in. And so for the future high rate manufacturing methods that we anticipate, we need to be leaders in thermoplastic composites. Mm-hmm. And so welding, how that relates to welding, we think welding is really key to realizing that high rate manufacturing, especially induction welding, as Wouter was describing, the high rate achievable there. And to apply welding, which is where the Spirit makes large structural assemblies. We've made small stamp form parts in the past, but our business is really in these larger assemblies where welding is going to be key. And since the material costs are rather high for thermoplastic composites still, we'll have to realize some of the cost savings through the consolidation of manufacturing steps. And so our strategy with thermoplastic welding is to reduce the number of manufacturing steps, design for thermoplastic composites so that we're reducing steps and maximizing the structural strength of these parts, and also to automate the processes. Mm-hmm.
Erik, can you relate to the strategy that Spirit is going on?
Yes, definitely. And I think welding is one of the technologies that really fits here, because we want to go for large integrated structures, we want to go for weight saving, and this is typically the process which can help there.
Yeah, great. Andy, you mentioned you're working on induction welding. Do you also explore the other welding techniques?
Certainly, yeah. Induction welding is one of the primary methods that we are pursuing with our R&T group. Resistance welding is another one that Wouter described as well. And conduction welding is another one. I don't think we talked as much about that on the show prior.
True.
One of the methods that we use at Spirit is called co-fusion, and it's a little different from the others. It is a type of conduction welding, but it utilizes a heated tool, heats skin, for example. So like a skin stringer assembly, it would heat through the skin side surface up to the frame surface of the stiffener that's attached, and no further. And we utilize strategic insulation to keep upstanding stiffeners on that skin from deconsolidating, from reaching temperature. So our goal, similar to induction welding and getting the energy exactly where we need it, is to bring through the skin and up to a fane surface to melt temperature, apply the pressure, using an autoclave or tooling. And in our case, Spirit has many autoclaves. And while we want to pursue out of autoclave methods, because we don't want to use high temperature, the high temperature is required for thermoplastic composites. That's pretty challenging for an autoclave. But considering we already have a lot of relatively low temperature autoclaves, we're able to utilize that a cold autoclave, so to speak, to do this type of consolidation with just conduction welding. So that's a little bit different than some of the other methods that were described.
Yeah, well, thanks very much for pointing out these as well. So yeah, thank you very much for this contribution.
Thank you.
Thank you, bye-bye. Erik, can you explain why we choose to focus on these 3 welding methods?
Yeah, definitely. Because as mentioned, we don't have to use an autoclave for these 3 processes, and that's a very good benefit. Because it's very expensive to use an autoclave, and that's something the industry would really not like to do.
Yeah, well, here we have an autoclave.
Yeah.
So that's also a benefit, right, from working together with the TPRC?
Yes, definitely. We have the facilities, but we are striving for out of autoclave for the future.
Yeah.
But we do need the autoclave for research that's on the processes that are used today.
It's also nice to see that, as we just explained, you just need heat, pressure, and time, and there's different ways to do it. And well, Spirit has now found a different way to apply heat and pressure to the interface and have a different welding technologies.
Yeah.
So making this decision is quite difficult as an engineer, but there's plenty of options, which is really nice.
Yeah.
Great. Well, thank you. And we're honored to welcome another guest to the show. We will talk to Francis Samelot, Associate Technical Fellow of Boeing Research and Technology. Welcome, Francis.
Hi, thank you for having me.
Hi, live in the USA.
Yes.
Great.
Actually in Puerto Rico, but also part of the USA.
True. Oh, thanks. Boeing invests a lot in research done at the TPRC. Why do you believe in TPCs for aerospace?
Yes, thermoplastic composites, as it has been mentioned in previous shows and in this show, they offer a lot of advantages in terms of reducing weight and cost because they're better suited for automation and having fast processes in implementation of them.
And why is welding so important?
Welding is so important because it's uniquely suited for this type of material. So the 3 elements have been mentioned, right? The pressure, the temperature, and time. For thermoplastic composites, once you apply this temperature, they can be reheated and reformed. And then once they're cool, they'll still be able to be used. So induction welding is a process that can bring in that heat in a localized way and take advantage of the material property to be reheated and reformed.
And
it also lends itself to automation. So it keeps building up on the advantage of thermoplastic composites.
And to what applications are you thinking of in the long term?
There are different applications that is suited for. There are edges, skin stiffened structures. And I think as the industry grows and there's a better understanding of it, also the application space will grow.
Okay. And what are the benefits of welding for the certification process?
The certification process will take some time. I think, as it was mentioned, there's still some black box element of it. So I think there needs to be a better understanding of the process to really certify how it should be, which is a unitized structure. I think meanwhile, relying on certification approaches that are understood and similar to other technologies would be the approach taken. And then as the confidence grows, as we have a fundamental understanding of the process, then the certification will approach more as it should be, as a unitized structure in itself.
Yes, so that will become a next step.
Exactly, yeah. But first we need to reduce risk and have confidence in what we're doing, so then we approach it like things that we already know how to certify. So in the beginning, it might look more like an adhesive joint, but that is not the final step. We just need a starting point.
Thanks. And you have been to the TPRC regularly. How do you like working here at the TPRC?
It's great, yeah. I think there is nothing like being there hands-on, being part of the research as it's being developed. There's a saying, a picture is worth 1,000 words. I think hands-on is worth 1,000 pictures. So working with an excellent team of researchers, and you get an understanding of the same language. And I'm not talking Dutch versus English, but the same technical language because you face those same problems together, and then they can bring their fundamental understanding to the table, whereas partners like Boeing can bring that industry perspective to be part of the solution.
Great. Well, thank you very much for sharing this story with us. Thank you. And goodbye.
Thank you.
Bye-bye. Well, Erik, what are the options for companies that want to work together with TPRC?
Well, we have three main options. So the first one is to become a member of the consortium of TPRC. There you can define what research is being done, and you can also benefit from all the roadmap research that's being performed at the moment. And secondly, you can also do a bilateral project. So when you don't want to become a member, but you do want to do research, we can define a research project together, but we can also work on characterization of material or development of tools. And in the last place, we also provide training. We have an introduction course on thermoplastic composites, but we also do an advanced forming course. And at the moment, we're also working on a course for welding of thermoplastic composites.
Okay, so it's quite a broad range.
Yeah, exactly. Yeah.
Great. Well, then whatever suits your needs or interests, I'd say.
Yeah, definitely. Yeah.
Very good. Well, you just finished your PhD. If somebody feels inspired about doing research here or working together here, what can they do?
Well, they can just...
What would you say to them? There's your camera.
Well, they can just contact me or visit our website and contact us via the website. And we'll be happy to look at your ideas and share different perspectives. And maybe we can work together and have a nice collaboration.
Nice. Thank you.
Maybe if I can add to that quickly.
Of course.
So we'll be looking for like 5 to 6 PhDs engineers at TPRC for the coming future for the Enlighten program. So if there's any student who would like to do a PhD in the Netherlands, please contact Erik.
Yeah.
Very good. Well, thanks. Noted. Let's go to the questions, the Q&A. While we were talking to the partners, we had these questions here at the table. The first one is, oh, that's a nice one. Of course, all the questions are nice ones, but when do we board a fully recyclable TPC plane? I don't know, there's no name or anything beneath it, but it could come from all of us.
Oh, that's a really good question. I'm not in a position to answer this. Probably we should probably contact Spirit or Boeing to answer this question. What we see is a lot of research on large structures in thermoplastic composites, so fuselages, wings. So people are thinking about these solutions. Big companies like Boeing and Spirit are working on these solutions. But for aircraft industry, it will take some time, of course, before we are at the stage that we can actually fly in a fully thermoplastic composite airplane.
Yeah.
I'm not sure whether Andy wants to comment on that. I see her in.
Hi, Andy. Maybe you can say something about that. When do you have any idea? Can you say anything about when we will board a fully recyclable plane?
Well, to be honest, it'll be a while. It is theoretically possible, but we're still moving from small parts to large integrated structures, and I think it will be a while, as Francis stated, with the certification efforts required to get to thermoplastic composite fuselage, for example. So we're going to start with there is some primary structure already flying today, but we'll have to slowly build up in a stepwise fashion. We'll start with less primary structure, bulkheads, some are and some aren't. And then maybe someday, with our sustainability goals that we have in mind, maybe someday we will have a thermoplastic composite fuselage. But I think that's quite a ways out still.
Yeah, there's a difference. We had a fully plane of TPCs and a fully recyclable plane. Two different things, of course. What do you think, Andy? Yeah. A fully recyclable plane?
Fully recyclable. Well, that is very ambitious.
That's me.
More of the primary structure, because that's what we make in Spirit. But there are all of the systems components as well, and the batteries that we have on board. Okay. I hope that the processes that we use to manufacture these components become more sustainable.
Okay, well, one bridge too far, fully recyclable, right? But when it comes to TPCs, you all are saying it might take a while. But if I say 20 years, is that a crazy thing to say?
I don't think that's crazy with regards to building up larger primary structures.
Wouter, do you want to add something?
Still before my pension, I would be happy. I mean, so,
Is it realistic, you think?
difficult to say. I mean, it will take some time, as Andy says. So,
Okay.
But let's work hard and see how
Let's
far we
work
get.
hard. Very nice. Thanks for this in addition. The other question from Ranish Hariharan. What is the effect of laminate thickness in induction welding? Erik or Wouter, who wants to take this one?
Well, the thicker the laminate, the more material you heat up. So it might become more difficult to extract the heat from the locations where you do not want it. So I think it would be easier to weld thinner laminates. But yeah, that's something we're figuring out.
Okay, great. The next one is from Emil Manga. How much influence does fiber orientation have on weld when it comes to quality and strength, or does it have any?
Probably it has. So that's something we want to look at the within the Enlighten program. So I talked about this microstructure, and a part of this microstructure is basically fiber distribution and fiber orientation at the weld interface. And we know this has a role and effect on the performance of the weld. So this is definitely something we need to look into as an industry and as a community in order to come to predictable weld performance.
Do you think this will be covered in the Enlighten project?
Yeah, it will. So it's we have got a work package in Enschede on that and in Delft as well. So it's something we will look at for sure.
Great. Okay. So to be continued.
And to add to this, when we look at the different processes, I think the fiber direction is particularly important in the induction welding process, because there the heat is generated in the material. So the material itself influences the way the heat is generated. Just like Maarten Bach told us that we need these current going around. And that's something where the fiber direction also comes into play.
Okay. The other question is from Sujit Ravikumar. How is the bond strength of the welded joints analyzed compared to the use of adhesives?
Well, we do different types of mechanical testing to characterize the weld performance. So you can think about lab shear testing, which basically we've got a small sample here, which are two laminates which are welded together, and we pull it apart and test what the strength of the interface is. That's one way. We can also do fracture mechanics-based testing, so measure fracture toughness. So we look at different aspects basically when we characterize weld strength.
Well, maybe we can bring in Maarten Bach again also to react to this question. Maarten? Are you there? Yes.
Yes, I am.
Did you hear the question? How is the band strength of the welded joints analyzed compared to the use of adhesives?
Well,
can you add something to Wouter's answer?
So what we typically do in the, let's say, the standard testing is indeed a single lab shear test. So then we test the shear strength of a blind, and another typical test is the L pull off test. So you have a skin laminate and then an L profile welded on it, and then we test how strong it is to pull off the weld, and that's a different kind of failure mechanism which is being tested. So these are the type of, let's say, industry standards being used and being tested now, and that's done by indeed companies like Boeing, for example. They also use these kind of tests in the qualification process.
Okay, well, thanks for this addition.
Yeah.
Great. Well, I'm so happy that we have such a broad range of expertise on this show. It's great. Well, the last question is from Patricia Vasquez. Talking about repairs for an AOG, for example, which technique would be more suitable and easier to apply? Erik, Wouter, who wants to go first?
Shall I?
Yeah.
So, I mean, we've been looking, of course, into repair using welding technology because you can locally heat and fuse materials, but it's not straightforward. So if you heat these materials, they may also expand a bit, which really complicates the process. So I would say as a first step, let's try to get to proper welding technologies and then see whether we can develop repair technologies. And it's difficult to say which one of these technologies would then be the most suitable for repair. I'm not sure whether Maarten Bach is still online, because I do know that they are working on repair technologies using their technology.
I bet Maarten is still online. Maybe we can ask him. Oh, there he is. There he is. Well, we have a great technical team here.
Yeah, repair is indeed also one of the topics we are looking into. We've done some research, especially with the fabrics, and there we've had successful results. And with UD laminates, we've done some initial testing, but with this regard, it's a topic we put on the let's say the technical roadmap for 1 or 2 years. So it's something we want to investigate, but first we need to fully understand those heat-up mechanisms to get the proper UD weld before we go into these repairs. So it's something we have, let's say, on the wish list, but at the moment we cannot fully focus on this application.
Okay. Maybe we can have Francis Samelot. Yes, there you are, from Boeing. Maybe you have something to add to that from your point of view. When it comes, let me repeat the question. Oh, okay, please continue.
Oh, yes. I was going to echo what has been said. I think viable repair techniques is something very important for the technology to mature, but I think we are still at the point where we're understanding the fundamentals and establishing the processes and how the different effective defects are generated for these processes. And that comes first. And I think once that's established, then going deeper into repair techniques for these type of processes is what will naturally follow.
Great. Thank you very much. So start with the basics, and in the future, it will all be cleared up, we hope.
Yeah,
We work hard for this, yes.
We work hard for this. Yes, great. Well, this concludes our very first or very third episode of TPRC Talks. And if you have other questions, please don't hesitate to send it to us, because these guys are very happy to answer them later on, right?
Yep, yes.
One-on-one.
Yeah.
Well, I hope you all feel inspired. I sure am. I'm very excited to start the Enlighten project and see what will come up in the next decade. The future is bright, or light, I would say. Well, fine. Erik, when it comes to induction welding, what would your vision for the future be?
Well, we see that the industry is going towards large structures, so that's where we need these welding technologies for all the integration of the single parts. And we see that our research is fundamental, and together with the industry, we can develop this whole process. Because at the end, we want to have rapid manufacturing and we want to be cost efficient. And I think that's where thermoplastic composites are ideal. So it's yet another advantage of thermoplastic composites. It's weldability.
Weldability, yes. Yeah. And Wouter, is there anything you would like to highlight from this show?
What I really like is that we've got quite a number of participants, so that resonates really well with the image I have that the industry is growing. And what I also really like that everybody is very enthusiastic. I mean, everybody on the screen is enthusiastic. In the studios, everybody seems to be enthusiastic. So there seems to be a very positive vibe, which really is inspiring. And I think the future indeed is pretty light, I would say.
Nice. We're going to end with this positive vibe. I would like to thank you all for watching. And if you have any interest in further developing the benefits of thermoplastic composites, then we are fully at your disposal. I would like to thank my guests here in the studio, Wouter Grauve.
Thank you.
And Erik Kramer.
Thanks.
And of course, our partners who joined, Francis Samelot from Boeing, Andy Meyer from Spirit Aerosystems, and Maarten Brach from KVE Composites. Thank you very much, together with our bright mind, Yannick Busser, of course. Thank you all for watching, and we hope to see you on board at the TPRC.